When we look at the universe, it's easy to imagine a quiet, still expanse. But the reality is a crowded, violent landscape. Massive galaxies collide and merge, using gravity to rip trails of stars from their neighbors. Most of the universe is arranged into the cosmic web, a network of dense filaments and massive clusters where galaxies are packed tightly together like commuters in a crowded subway. This crowding creates a problem for astronomers: environmental noise. In these dense clusters, galaxies are constantly harassing one another. They steal each other's gas, their gravitational pulls warp passing disks, and the turbulent environment strips away the raw materials needed for new stars. Over billions of years, this physical interference overwrites a galaxy's history. When we look at a battered galaxy in a crowded cluster, we cannot tell how it would have evolved on its own, because its shape and chemistry are the results of external collisions. To understand how a galaxy works based on its own internal physics, astronomers have to strip away that noise. They have to find a galaxy living in total isolation. To find one, we look away from the glowing filaments into the pitch-black spaces between them. These are cosmic voids, immense pockets of space stretching hundreds of millions of light-years. Zooming deep inside one of these dark hollows, we find a single isolated system. This is a void galaxy. It sits like a remote lighthouse in a cosmic desert. While a typical galaxy might have dozens of neighbors nearby, the nearest companion to a void galaxy can be millions of light-years away. By surviving removed from the chaos of the cosmic web, these systems act as a control group. They give researchers a look at galaxy evolution in its purest form. What happens to a galaxy's development when the universe simply leaves it alone for billions of years? The primary advantage of isolation is resource hoarding. Galaxies run on cold hydrogen, the raw fuel required to ignite stars. In a crowded cluster, hot surrounding winds strip that gas away. But out in a void, a galaxy keeps its cold hydrogen reserves intact. This hoarding changes how the systems age. While crowded galaxies burn through their fuel and settle into a quiet, red retirement, void galaxies use their reserves to churn out young, blue stars long after their neighbors in the web have gone dark. Isolation also preserves physical structures. Without the gravitational pulls of passing neighbors to tear at its edges, a void galaxy can maintain perfectly symmetrical spiral arms over immense spans of time. Even in total isolation, the internal machinery is still churning. Massive stars live fast and die in supernova explosions. Gas swirls inward, feeding central black holes and sending shockwaves across the stellar nurseries. These internal processes continue despite the isolation. The surrounding neighborhood is quiet, but the galaxy remains an active engine of change. This split-screen model separates nature, internal physics, from nurture, environmental damage. Look at the void galaxy on the left. If its disk is warped or a dense bar forms at its center, we know that structure was caused by its own gravity and spin. On the right, in a crowded cluster, that same warp is impossible to diagnose. It could be the result of its own spin or the scar of a collision with a neighbor 5 billion years ago. By removing the variable of neighbors, void galaxies allow humanity to read the baseline laws of galactic physics that are usually hidden by the crowd. These lonely systems also provide a way to map the massive hollows that surround them. Astronomers use them to answer a difficult question: how do you measure a space that emits no light? In this dark matter grid, void galaxies act as physical tracers. By tracking their isolated positions in the deepest basins of the universe, astronomers can map the invisible topology of dark matter and measure exactly how these voids are expanding. They also expose flaws in our models. Computer simulations predict that voids should be full of tiny dwarf galaxies, yet we find far fewer than the math demands, a discrepancy known as the missing satellites problem. Void galaxies are a stress test for astrophysics. If our theories about how the universe builds structure are accurate, they must hold up in these starved, extreme margins just as well as they do in the dense centers. Voids are growing, active environments where galactic evolution unfolds at a whisper instead of a shout. These systems prove that gravity doesn't need a crowd to create order. Given billions of years of solitude, a galaxy will patiently build a complex, stable, and perfectly symmetrical structure entirely on its own.